good evening, or afternoon, I guess it still is. This is a shot of the Great Lawn and Belvedere Lake in Central Park. We're fortunate enough to work on, and we'll talk some about it. It was probably the most complicated project I've ever done, as well as one of the largest ones. But all this work on soils, when I got out of school, I got involved with a lot of folks across the country that are involved in the Metropolitan Tree Improvement Alliance, or METRIA. And these are some of their folks. Phil Krall is from Syracuse, New York, and was sort of the father figure of the group, and I was the youngster of the group. And Jim Patterson was with National Capital Parks in Washington, D.C., and was dealing with all these horrendous compaction issues and on the National Mall. And so we were looking at and would meet each year and discuss how to deal with these problems. And we soon realized that we had to actually conquer these problems with soils in order to make great landscapes. And when we didn't conquer them head on, what we ended up was either landscapes that failed or landscapes that really didn't perform well. This is a kit we had for this urban workshop, and that's on the National Mall. And you can see the layers of loam and clay that are put into the mall. And it's a lot of pretty nasty soil. Not something conducive to trying to grow grass or trees. Well, the next year, the Vietnam Memorial opened on November 10th, 1983. The day after, they closed the Vietnam Memorial in 1983 because it had rained the day before the opening, and the entire landscape and hillside was totally destroyed by the crowds that showed up. It was like running a herd of cattle through a wet field. We had to start over. It's that simple. So from that day when I was up there with Jim Patterson, we both said, we're gonna find solutions that can be installed in landscapes when they're first built to overcome the various kinds of problems. And this is also several years after Constitution Gardens failed, because 3/4 of the trees sank in the tree pit, because the way landscape architects would show tree pits in their details doesn't work, especially when you have soft or loamy or clayey soil. They just sink down in the mud. So in 1984, the three of us were asked to come up to New York City to the Great Lawn and asked to do a charrette, a technical charrette, to figure out how to fix the Great Lawn. I first walked out on there and said, this is not normal. This looks like a landfill, and it's exactly what it was. It was a landfill put in by Robert Moses era in New York City, and this they filled in an old reservoir with a lot of rubble and debris and 2 feet of soil over top. And so they had compaction problems. You see a little green out there, that's weeds. There was no grass out there. The whole landscape had no drainage in it. It would all erode and run down, and the pond here at the bottom, Belvedere Lake, was almost totally filled with sediment. So the whole place was just sort of a disaster. People still played softball out there and did some various activities, But when they would have the New York Philharmonic come out to do a weekend show on the mall, if it was dry that day in the summer, it'd be Dust Bowl day. And if it rained anytime, several days or even the day before, it was Mud Bath Day. So it was really terrible conditions. And so they asked us to solve that. And so we started in the early 90s. Our firm got the contract on it, and we designed a whole new soil system and a whole new Belvedere Lake. And that's been in now 23 years, working beautifully. And what we do is we basically use soil physics tricks to be able to manage the whole landscape and how water moves in it. We can handle in excess of a 100-year storm event without any runoff, and we can keep moisture in the soil for the plants. And we have enough capacity, we can store over 1 million cubic feet of water in that landscape before we have any runoff that occurs. And that's in excess of a 100-year storm. So we put down some standards that we thought were reasonable design standards. One was we wanted to have the site be able to handle a 100-year rainstorm event, which is about 12 inches in New York City, infiltrate it all, let it move down so that if the storm is over 3 hours before a concert, like put 1 million people out there, as well as 3 semis to open up the stage for the New York Philharmonic and not have any damage to the landscape. The Central Park Conservancy said, "You're crazy." I said, "Well, I might be, but we're going to do that." And they ended up signing on to that, as well as a number of other standards that we laid out. So we looked at the wettest, most extreme wet condition of record in the climatic records, and we look at the driest events of record, and we create a soil that solves both of those two issues. Everything between then works. We just have to solve both ends, and we have to do it in the same soil. That's why we use soil physics tricks. And here's Belvedere Castle overlooking Belvedere Lake. We're currently working on, right next to this, Delacorte Shakespearean Theater, where we have to lower the water table about 10 more feet. And I worked with the Manhattan Sierra Club and Audubon Society so they wouldn't sue the city again. And they liked it so much, they were really trying to protect dragonflies. We doubled the amount of species out there and the number of total dragonflies. And so there's a poster that was made by all three together signifying how that design works so well. And this is Delacorte Theater as it exists today, right next to it. And we hope to next year have under construction a new theater at that site. This is down at Battery Park City Authority, which is a redevelopment area down right next to Battery Park. And this was the first section of Nelson B. Rockefeller Park that goes up the Hudson River. We were not involved in the design of this. We got involved when the landscape failed, and we represented Battery Park City Authority in dealing with the architect and landscape architect, and ended up settling out of court to get the system corrected. The design person, landscape architect, did a great job of designing it. During construction, their staff was no longer with the firm, and they didn't understand the complexities of what was being done. And so it ended up being built incorrectly and failed. This is the new one. We, 2017, received the award from ASLA for the main fountain garden at Longwood Gardens. This involved a total rebuild of about 5 acres at Longwood Gardens. Everything you see there, the sculpture pieces, and were original. Some were broken, some need to be repaired, some replaced. Everything was taken away. New ones were made in Italy. Then they came back. Pierre Dupont, that used to own this as a personal summer residence where you'd have families and big events, had started this when it was originally built in 1914. So it was in a pretty bad state of disrepair. I was involved as the soils person to work with the design team on coming up with a soil that would do big rainstorm events and would also hold moisture and would also not be disturbed by people on it. I don't know how many people were there that night when you were there, Brad.
It seemed like 20,000.
That's a lot of people on that lawn. It's fairly small, but yeah, could have been. This is another shot of it. Another one. Anyways, beautiful place. If you've never been to Longwood Gardens, it is gorgeous and really worth a visit. It's south of Philadelphia in the southeast corner of Pennsylvania. We currently have under construction this project with Gary Partners and AECom, and have closed Maryland Avenue to expand out and make this small park area larger, but we're going to maintain that vista. And so it's very creative solution by Gary Partners, because they're running out of good sites for memorials. This was a shitty site. And Gary Partners made this into a very nice workable site along with AECom. This is shot just from a couple weeks ago, and you can see through here section of Maryland Avenue where we put down the lower portion of the soil profile in and are building that up, and I'll be up there next week to make sure everything's going well. Because they're moving in some big box trees, we needed a 4.5 foot deep soil. We normally don't build them that deep. We did for some portions of Longwood, and we're doing it for this project. This one, we can actually store in the soil after a rainfall event, assuming you have one big enough, but it will store and hold about 1,000-year rainfall event. So we could design for big storms. When they had the large hurricane event several years ago in Houston, most of our sites could handle a rainstorm like that without having any runoff, and it would drain out through the bottom. We also just started construction on a restoration and redo of the National Air and Space Museum for the Smithsonian Institute. It's right on the mall, actually right across the street from the Eisenhower Memorial in Washington. This is a project we did in Raleigh. for the Art Museum, worked with Civitas out of Denver, and with Stewart Engineering, Landscape Architects in Raleigh, North Carolina. And this was finished up a year ago. This is a active area for events and weddings, and lips in the middle. And a lot of grasses, a lot of trees, and a lot of my friends like to go and walk through this, and it's part of a larger park, but it's the new entrance to the park, Sculpture Park. And we just finished up a month ago with Sasaki, a park in downtown Raleigh, one of the old historic parks, squares, and everyone sort of knew what we were going to do and how the soil was supposed to work. We had to preserve all the big oak trees around the perimeter and handle those totally differently. But in the middle, we created new soil, and it rained the night before the ribbon cutting and had a torrential storm down there. And some of the staff were a little worried, well, what's it going to be like in the morning? Well, they said, you know, right after it rained, we walked out there and the whole lawn panel was dry. So it was going to be perfect the next day, but it was perfect then too. This project we worked with on a limited basis in California, San Francisco, on the Presidio tunnels and parkway that connects into the Golden Gate Bridge. They were looking around the country trying to figure out how to build a 7-foot deep horticultural soil with heavy equipment without over compacting the soil to meet their specs. And we showed them how to do that. And there are very few people that have done those successfully. They were really going to have a contractor build these layer by layer, build it up 7 feet. Then they were going to check it, inspect it, and if it wasn't right, they would have to dig it all up and start over. And I said, that's dumb. Let's make sure it gets built right the first time, each layer you put down. So how do we design with climate change? We're going to have more rainfall in the southeast. We're going to have more hurricanes. We're going to have more heat. And we're going to have more severe rainfall events and hurricane events. So we're going to deal with a lot more water in the future. So my way of thinking about this is that on major public projects, we need to design at minimum for a landscape that will be sustainable for at least 100 years. So we need to think about what is going to be the climate in 100 years and how we going to manage and design our systems. So extreme rainfall events, we can look to historical records and look at the worst possible events. We've done that for 30 years on projects. We use a drain mod program that's a free program that has very heavy data inputs you have to put in. But we use that up in New York City for the Great Lawn to figure out how much we could infiltrate, how much we could store. And also we used it to look at the worst case drought conditions, how much we need to irrigate. Probably most people will tell you around here that, you know, about 1.5 inches water a week would be really good. Not during a drought. We need in New York City and most of the East Coast about 3.8 inches a week. Or we're going to have the landscape going into stress. So do we want to design enough capacity to keep it out of stress? Or are we going to go into stress and destroy a lot of the landscape that we put in? So we use that to figure out worst case conditions. We're also looking at NOAA and some of their projections for the next 100 years. And it's really a rough projection right now. But we might increase rainfall events by as much as 25%. So we push it up and do maybe 25% more. And I'm in discussion with some other professionals in the country where maybe we should be designing for more than 100 years. We haven't really decided that yet. We also use the same programs to assess work I do as an expert witness in federal court. And we did a big project for the United States Department of Justice out on the upper Mississippi River, where we used 53 years of data to be able to prove that the Corps of Engineers did not damage some agricultural drainage districts behind the levees. They claimed that there was more seepage through the levees and that their crops had failed. And so the same techniques we use on the Great Lawn Central Park, we use out here in a court case and model it and look at exactly what's happening. We can do that on a daily or hourly basis over, in this case, 53 years of records. So we've done these various projects. The first two dealing with mainly drainage. These are expert witness cases. We did the Cheyenne River case dealing with sedimentation. And we're currently working on for the Wetland Preservation Foundation in California, Northern California, where they've sued the California Division of Water Resources and the Nature Conservancy because they're not adequately preserving the areas in what's called the Delta, where most of the water in California flows to before it goes into the bay in San Francisco. So they're wanting them to avoid having these environmental impacts in the Delta region. So if we use that same stuff on these kinds of projects, and the second two projects we've gotten into infrastructure, where you have a large park that's built over a freeway or a park that's built over top of a basement that has no heating. We use and do a looking at worst case conditions of high temperatures in the summer in terms of what's going to impact soils, as well as low temperatures in the winter. So these are typically in planters, and we usually have installation, and we do a number of different things, but we can keep and figure out how to design all that with a model. Well, it's basically a heat transfer model that's used in buildings, but we've modified it to use outside buildings and soil. So, goals we have for sustainable soil design is, one, design for 100 years. We want to be able to have these venues resistant to a lot of people, and people typically destroy parks in large urban venues. And we want to have it infiltrate the water, and we want to make sure we deal with temperature issues. So all those are the elements, other than hurricane prediction, that are going to happen more and more intensely in the future. So How do we do that? Maybe you've seen a textural triangle like this, but down in this corner, we have sand and loamy sand, and a little bit of sandy loam. When we operate down here, we can do what we call sand-based structural soils. So we have sand, then we have some topsoil that's mixed together. If we do it right with the right kind of sand and we limit certain types of equipment, we can do this and build large landscapes with heavy equipment and keep them from being over-compacted. Other types of designs we do other than sand-based structural landscapes, we use the gravel-based structural soils for the CU soils or Cornell soils. And we do various types of other soils that we use for various purposes. Sometimes we have as many as 7 or 8 of these different soils for different functions in the landscape on just one project. So the way we do this is we have all these different sizes of sand that we have. We like to use coarse and medium sand. We prefer not to use anything coarser. We prefer not to use any fine or very fine when we're just buying a straight sand. There are 2 kinds of sands that you have that you're going to be able to find out in the market. Well-graded sands that have everything in it, from very fine to coarse. And the particles packed together, has low porosity, very small effective pore diameters, and it typically goes by the name of concrete sand. Makes good buildings, good mortar, good concrete, bad landscapes. So, and of course it's the cheaper kind of sand, so contractors want to always use that. So we're always going, no, you can't do that. We want a uniformly graded sand that's good for infiltration. It really is very narrow range, just medium and coarse sand, and a little bit more else might be above and a little bit below, but we want to have it screened and washed and be the kind of material that will make for us a good landscape. So let's go through my simplified principles of water movement soils. Now pay attention, because I'm going to give you a little quiz after we go through these, okay? First, principle number 1. Now the situation we're doing, we're going to have a sandy mix, so it'll be sand and some topsoil mixed together, and it'll be a layer over top of a fine gravel. And this is going to be totally saturated, the soil, the sandy soil above. So we're going to have atmospheric pressure in the gravel through the drain pipes. And because it's fully saturated, the sands, they're going to flow in proportion to the size of pores head and slowly drip into the gravel layer below. Now, so when it's all atmospheric pressure and it's all saturated, water will be up here in this sandy mix and they'll drip, drip, drip into the gravel. As soon as it goes to a negative pressure, which is what we want it to do, it's going to stop dripping into the gravel. And all that water is going to be held for the plants. And then eventually, if we don't have irrigation that kicks on, it'll get out perhaps and no rainfall to the wilting point. We don't want to do that either. So when it's saturated, it flows just like flow of water in a pipe. We just have smaller pipes in here. So the same principles. So again, we've got sandy soil over gravel layers. They're both saturated. So our uniformly graded coarse and medium sand will always conduct water faster than a concrete sand, because we don't have all that fine sands in there plugging it up. Number 3, we have situation, the same thing with a sandy soil over top of gravel layer. And the gravel is an atmospheric pressure, but not the sand, because the sand is what we call unsaturated. Might be wet, but it still has air in that soil. And when unsaturated, the flow of water in the soil slows to a very slow hydraulic rate. It drips very slowly or doesn't drip at all. So what happens is flow rates are very high at 0 or total saturation. But once you back off that a little bit, they plummet down and they start draining very slowly, which is what we want. We want to drain enough to let air back in the soil, but we don't want to have all that water flow out of the soil. So principle number 4, when unsaturated water stops flowing into the gravel layer due to a greater soil moisture tension in the sandy soil. The sandy soil no longer has a positive pressure, it has a negative pressure, and water will not flow into the gravel. Water will be there, and the plants can use that water, and we can have maybe as much as 35% plant available water stored in that soil. So a tremendous amount of water we can store in these. And then in addition, when it's unsaturated, water always flows in the direction of the greatest negative pressure. Water will flow, but it will very slowly flow into the smaller and smaller pores and penetrate all the smaller areas in that. The sand will open up and be a lot of air movement in, and that's what we want too. So up here, we're a little less than 45% of the mass of the soil is water when it's saturated. And then if we allow drainage to occur, and it will drain down to a point here where if it's 100% sand, there's not much left. If it's over here at 75% water or 75% sand, we're going to have a lot more water in the soil before it gets down to a wilting point. So we can adjust the percent of sand and topsoil as to how much water we want in it. So in the southeast, when we typically have more moisture in our soils, we can hold more moisture by adjusting our mix. When we're in the southwest and we're in more of a xeric landscape, we may not want to hold as much water. So we can adjust that for different climates. So principle number 5, when unsaturated water is held in the uniformly graded medium sand and coarse sand more than the well-graded sands or concrete sand. So again, we don't want to use concrete sand. We want to use the very finely graded select sand. And number 6, we're going to change the beginning points up here. Sandy soil, we're not going to put over gravel. We're going to put it in a trench or in a bed over top the loamy or clayey layers of soil. So going outside here, if we just dig down in the clay and have this nice sandy mix sitting in there, when unsaturated, water will continue to drain from the sandy soil because the underlying loamy and clay soil has a greater soil moisture tension. So water is going to move out of our planting soil into the subsoil because we don't have a positive pressure or pressure break down there like we do with the gravel layer. And in this case, when we have it in that situation, water, once it's saturated, it starts moving. It'll just move all the way down to here, and everything will drain out of that sandy soil. So these are our principles. When saturated, water flows in proportion to the size of the pores, the head, and drains readily into gravel below. And then a uniformly graded sand rather than a concrete sand is going to work for saturated conditions better. When unsaturated, the flow of water in the soil slows. And number 4, when unsaturated, water stops flowing into the gravel layer. And number 5, when unsaturated, more water is held in a uniformly graded versus a concrete sand. And then number 6, when unsaturated, water continues to drain from the sandy soil because of the underlying loam material below. So here we are, New York City, Central Park, the Great Lawn. We're going to put in 25 acres of a soil profile. Which soil profile will drain the fastest when fully saturated? Profile number 1 has medium sand, then it gets coarser and coarser here. Profile number 2 starts off coarse, it gets finer as you go down. Then you have one that's a concrete sand here over coarse sand. They all drain freely at the base. Which one do you want to put in Central Park? How many people think number 1? How many want number 2? Any takers for number 3? Number 1 is the correct answer. Let's change. Y'all are a good group. Usually most people fail this. So we're gonna have the same 3 profiles, but we're gonna change the question at the top. Which profile will hold the most moisture after initial drainage? So you allow it to drain a little bit for an hour or 2, which is going to hold the most moisture for the plants at the highest plant available water. How many people think number 1? How many number 2? How many number 3? The correct answer is 1. So for both questions, the same soil is the best. That's our solution. Because we want it to work for both extreme conditions. We want it to have high plant available water, but we want to drain excess water out, and we want to be able to effectively handle big storm events. So that's how we're doing it basically. More technical in terms of getting everything to work, but that's the basics of it. So this is a layered system, and those layers work because we're creating a positive pressure at the bottom and a negative pressure in the planting medium up above. And we use some various factors. We don't use fabrics in it. We're going to have a bridging factor to make sure the sands mix sits over top of the gravel. We have a uniformity factor and a permeability factor for those. So we end up with medium coarse sand mixed with topsoil in it. We have fine gravel. We make sure this bridge is over top of this. It doesn't fall in. If it falls into the gravel, it doesn't work. We have no filter fabric. It's the first thing it'll clog, and then your system fails. And we have ADS pipe with no sunk on it because that will fail. And in this case, we had a landfill cap and then rubble underneath because the landfill went 35 feet down. So that was our basic solution. 23 years, still working. Does a marvelous job, but it takes a team to make sure the specs are right, make sure the design's right, etc. If you want to give me a card or trade cards at the end, I'll send you a publication. If you're a member of FASLA, you can get it on their website, or I can just send you one. But it's about 83 pages and it explains all this, plus some other kinds of strategies for landscapes. We've got a few more minutes. Here's our newest thing I'm going to show you. This is sort of optional at the end here. What we've done, we've had a couple clients that have asked us to sterilize the soil for an entire landscape. We sort of went, you really want us to do that? It's expensive. So here we have a sandy loam topsoil that's been run through a rotary kiln. So it's been there for about 15 minutes, and it comes out in these little BBs. And we have a medium and coarse sand, and we mix them together, about 80% sand, 20% silt. Yeah, the silt loam pellets. And these will soften up and spread out a little bit, but you're still going to have a lot of pathways through this sand, so you get fairly high conductivity rates. The water moves through rapidly when saturated. And then we put this on top of a gravel. We've got a choker sand, next layer goes down, and this is the planting medium up on top. This is all processed at a plant. Sometimes we use 2 plants to do it. And we mix it together and have it stored, ready to use on the project site. This is a slow process, so it takes us about a year for a big project to do this. And so what we have is, I've talked about this soil moisture tension, and this is in centimeters of water. And these are negative pressures down to wilting point. But we like to operate up here where there's plenty of moisture. So if it becomes saturated, after saturation, water will flow out, and somewhere in here it'll stop flowing. And we can actually set that rate as to when it stops. At a ASLA conference last year, annual meeting, I explained we put natural bioswitches in the soil, millions of them. And when it gets down to about 35% moisture, plant available water, they all click, 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 click across the landscape, and drainage stops. And the head of Brightleaf was there, contractors was there at the thing, and he was like, you mean you can make it stop draining? I said, you could never over water this site because it will always drain. And then if it gets down lower, you can kick on your irrigation. So these are the pore sizes that we're operating in terms of millimeters, and their equivalent size, if you think about sand, it's in these range of where we're trying to have our sand sizes. So when we get larger size sand, then we'll have larger pores, and smaller sand, we have smaller pores. And we want to have them in that upper area. So hydraulic conductivity from 14 down to 0, different mixtures of 100% sand versus 50% sand and 50% topsoil. We get slow conductivities here. We get very nice conductivities up here. Right now we're designing Site C where 5 to about 10 inches per hour of conductivity when it's wet, you know, on the size of storm events we want to deal with. And when we just have screened topsoil mixed with sand, we have a curve like the blue one. When we do these rotary kiln and these pellets, we have one down here, which means we could theoretically put about 15 to 20% more topsoil in a mix and still have the same conductivity. So more expensive the more pellets we put in, but it gives some options. Plant available water. We typically in these soils are going to be somewhere 22 to maybe 34, 35 at the tops of how much we would store in water. And we could select that and adjust the mix, do samples in the lab to make sure we're achieving what we want. And so we can do that very scientific basis. So anyway, that's how we're doing these big landscapes. We're also doing other kinds of soils, but this is the one that I think most people have generally been interested in because it applies to a lot of urban sites. Questions?